Welcome learners. In today's lecture, we are going to continue our analysis of the third chapter from the main textbook. And in today's topic, we are going to learn about Gauss's law. We are going to look at few examples of the Gauss's law, and we are going to mathematically prove the generalized form of equation presented by Gauss. So, what is Gauss's law? So Gauss's law basically states that the electric flux passing through any closed surface, again the important point is highlighted over here or underlined to be precise, the electric flux passing through any closed surface is equal to the total charge enclosed by that surface. This is what Gauss's law presented, and you can see the statements are almost similar to Faraday's law, which explained that the electric flux is equal to the total charge present inside the inner sphere. Then Gauss said that the simplified generalized equation is that the total electric flux is also dependent upon the charges in a surface where the accumulated electric flux is represented by the electric flux density. And then he also presented that the total charge enclosed is represented by the total elements inside a closed surface with electric flux density D, and it can also be represented by a volume charge closure as well. So the total charge Q is represented by both these set of equations, that is for the smaller region and integrated over a larger region, and this is what the Gauss's law presented. So let us go into this Gauss's law step by step and understand how these equations are formulated. Gauss's law basically presented few points that made him stood out, and these points were basically taken from Faraday's experiment. So we can say that Gauss's contribution was as follows. Number one, he presented a more generalized form mathematically, to be honest, mathematically compared to the Faraday's law. So it was a more generalized equation. Second thing he did is that he proposed that we don't always need no need for two spherical surfaces, as we saw with the Faraday's experiment. No need for the two spherical surfaces to find the electric charge, rather a single Gaussian surface will do the job. So Gaussian surface is basically an imaginary surface, and the electric field is always normal from that surface. So this is what Gauss said. He said we don't need to have always two sphericals or two spheres to see the electric flux forming. We can just take any object that has a charge and we enclose it by a Gaussian surface, and then it will do the same job. And finally, he also said that the enclosed Gaussian surface can be of any nature, can be of nature like a line charge, volume charge, surface charge, or even a point charge. So this is what Gauss basically said. So if we go back to the definition of Gauss's law, it said that the charge enclosed by any surface is equal to the total flux passing through that surface, which means that so the electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So what is a closed surface and what is a enclosed surface? So let us say if I take any sphere as what Faraday did in experiment, that has no boundaries, no cutouts, nothing. It's a complete piece of ball, a metallic ball. So this is considered as a closed surface. It cannot be penetrated. But what is an enclosed surface? Because the definition is focusing on closed surface, which we just saw, and an enclosed surface. So enclosed surface is, for example, if you take a cup of, or any cup, and you have a liquid inside it. Now this cup is open from the upper side. You can pour into this any form of a liquid. Now if I seal the opening of this cup with a plastic sheet, Now I can say that this club is closed, but in more simpler terms, it is an enclosed surface. So enclosed surface means that something which cannot be penetrated, but inside the liquid or solution, for our example, can move freely. It has certain space to move inside. So enclosed will have certain space or volume inside to move, but it cannot be penetrated, or you cannot enter unless you make a hole inside of this. So this is an enclosed or a closed surface, or the difference between them. Then Gaussian or Gauss basically said that if you take any charge and let's say you enclose it with an arbitrary Gaussian surface, so this is an arbitrary Gaussian surface, so the amount of energy that is being released in the form of flux lines will be same that is the amount of charge being held. And another thing is that on this Gaussian surface the electric field will always be normal to the surface. So whichever point you select, the electric field will be normal to that surface. So this is what the Gauss's law proposed. And in this arbitrary surface you can have a line charge, you can have a sheet charge, you can even have a volume charge or a point charge. So anything can be enclosed inside this Gaussian surface. For example, if you have any key and it is having a certain charge, you just enclose it with a single imaginary Gaussian surface, and then you can find the amount of flux lines that is moving through these Gaussian surface because of the total charge present inside this key, which is enclosed inside the Gaussian surface. This is what the Gauss's law presented. Now what was the generalized equation that Gauss presented? So the generalized equation is that electric flux can also be represented by a closed surface having electric flux density on that surface and the small portions in that surface d of s, and it is always going to be equal to the charge enclosed. So this middle term is what Gauss introduced and made this electric flux equation presented by a Faraday law into a more generalized form. Now let us see how this equation normally works, or basically understand how the equation is formed, and then we can mathematically prove it as well. So in order to understand this, let us assume that we have an arbitrary surface, Gaussian surface, and it has multiple amount of point charges q. Obviously it is going to radiate energy in different direction. Individually each charge is going to do. Now let us select an arbitrary small space inside this bigger surface volume charge. So obviously the electric flux that is generated from charge q is going to pass through this surface. Let us consider a point P over here, and we want to see the accumulated effect of all the flux lines that are passing through this point P. So we represent it, let's say, by a value of electric flux density on this surface d of s. We also know that whenever we talk about charges on a sheet or a surface, the unit vector is always normal to that, and then there is an angle formed between them known as theta. So this is the arrangement that is going to be available on this small piece of patch inside this bigger Gaussian surface, and then we want to see how can we prove this equation visually first and mathematically afterwards. So what we did is we considered a Gaussian surface where all the electric field lines are normal to this surface. Then we selected a small surface, let us call this d of s. Inside this bigger area, we know that the electric flux lines are crossing from charge q to this small patch, and they are represented by the electric flux density d of s, and the unit vector is always normal when we are talking about sheet distribution making an angle theta. So this d of s, which is the small area selected, can be written as that it has smaller portions and a unit vector which is normal to it. So this smaller portion is basically, you can assume that it has smaller sections inside this smaller patch d of s, and then the electric flux density that is passing through this surface is equal to the smaller amount of electric flux per unit this surface. So we can say that this electric flux or the differential flux is equal to the electric flux density and the smaller area inside this d of s. Now what is this d of s? Obviously d of s is going to have its two components. So we can say that it is going to have a normal component over here in the horizontal and vertical axis. So I can represent this equation in terms of its component of a vector. So the electric flux is equal to ds normal component. It can be horizontal or vertical with the smaller area d of s. And then we know that whenever the normal component is formed, so let us understand this by choosing another color. So let us say I have taken this as the normal component to this vector d. So this is d of s. Now whenever we have one vector and its projection is to be observed on the other vector, we know it's a scalar product. So we can say the dot product of between these two vectors can be represented as ds, and the normal component is making a certain angle theta, so it is represented as cos theta with d of s, and this turns out to be nothing but the dot product between two vectors. So hence we can see that the small electric flux is equal to the dot product between the normal vector d of s and the smaller section inside this patch, which we call as d of s, which we have selected. So finally, if this is the smaller representation, the whole area or the electric flux of the bigger Gaussian surface is we integrate this d of s over a closed surface, and this is equal to the total charge enclosed by that surface. So this is how visually we saw the electric flux represented by the Gaussian mathematical expression, and that is equal to the total charge enclosed, and hence this is proof. Similarly, we can also prove that our equation is also equal to the volume charge distribution. So we can also prove this portion of the equation as well. How we can do this? Again, if we select any arbitrary surface, and let's say a Gaussian surface, and it has different charges, let's say q1 represents the point charges, q2 represents line charges, q3 represents a sheet of charge, and q4 represents, let's say, volume charge. So how can we find the total electric flux of this? Obviously we can use the law of superposition principle, which means we can add all the charges inside this imaginary Gaussian surface, where we know that q1 is the sum of the point charges, q2 is the sum of the line charges, q3 is the volume charges, and q4 is the surface charges, rho of s, d of s. Let's say it's a closed surface. Okay, so this is how we can find the sum of all the charges. And finally we can also say that electric flux density was represented as a closed form of electric flux in a small patch, and this can also be represented as a volume charge distribution as well, because electric flux can flow inside all of these points from one point and emerge out from the other side, which means that if I select a volume charge distribution, let's say if I select a volume charge distribution, this volume charge distribution can encompass all the immediate charges. Like I can have a point charge inside this volume, I can have a line charge in one part of this volume, I can have a sheet charge, let's say on the z-axis, and I can have a volume as a whole charge. So this means that electric flux can either go through this point, it can cross the line, it can cross the sheet, and it can obviously cross the volume as well. So this means that the electric flux can also be represented as total volume charge distribution, that again depends upon the charge inside, and that charge can be inside this volume shape on a closed surface as well. So this is why we basically utilize the Gauss's law for the charge enclosed in these two forms, either using this part of the equation, or it can also be represented as this part of the equation. Whenever we have various charge distributions, we can use this portion of the equation, and when we have only a closed surface charge or a sheet charge, then we can use this part of the equation to find the electric flux, which is based on the total charge enclosed. So now let us mathematically prove the equation that it comes out to be as such. So basically the idea is we want to prove that the electric flux is equal to the total charge enclosed in a surface, which is equal to Q. So this is what we want to prove. So we have basically a left hand side if you want to prove this, and we have a right hand side for the electric flux equation. So in order to prove that, we assume that we have a point charge. Let us say we have a point charge at the origin of a spherical coordinate system, at the origin of a spherical coordinate system, and the radius in this scenario for the axis r equals to a, because we know for the spherical coordinate system we need to have a value of r, theta and phi. In this case r is equal to a. Theta and phi will remain their limits at 0 to pi and 0 to 2 pi. So this is the scenario that we have built up for our analysis in order to prove this equation. So let us prove these equations, left hand side and right hand side. So we draw this structure first and then we'll begin with the proof. So this is y, x and z, the right hand coordinate system. For the spherical coordinates, we know this is the complete visualization of the spherical coordinate system, where this is your phi, this represents your theta, this is your origin, and we can have any value of radius r. So obviously if we want to extend this r, it can go or be represented as an electric field intensity, or in other words it can be an electric flux density d of s, with d of s selected as a surface, and we can also have a unit normal vector over here, which is the a of n. The charge is in our scenario placed at the origin, and we want to do the analysis for a single point in space. Let us say that point is, or that patch area. Why we need a patch area? Because we need to figure out what is d of s. So let us say we consider a patch area over here. This is our patch, or a small surface that we have selected, which is our d of s. So this means that our area of interest will be such. So this is the area we have selected in our spherical coordinate systems, and this is the patch with radius of a, and we want to see what is the electric flux density in this small area, because we want to prove this equation. So we know that if we start with the analysis and we know the electric flux density of a point charge is given as such. So for a point charge, because our analysis says that we are considering a point charge at the origin, so a point charge electric flux density is given as q divided by 4 pi r square into a of r. So since r is represented by a, so I can replace r as q divided by 4 pi a square into a of r. This is the unit vector, so this is a complete vector representation. So basically we are starting with the left hand side. So in the left hand side we need to solve this equation. So we found the value of electric flux density, which is d of s. Now what is d of s? D of s is this small area selected inside this spherical coordinate system. So since this is the incremental surface area, so we know for the spherical coordinate system d of s, so the value of d of s for r is going to be r square sine theta d theta d of phi with the unit vector a of r. So now we are basically finding a surface area along r, and you can see that this is the value for the differential area for the spherical coordinate system. Now I can replace r with a square, and then the remaining equation remains the same, sine theta d phi along the ar unit vector. Now incorporate everything into the equation. So the left hand side equation comes out to be integrate over the closed surface S ds dot d of S, which is equal to, so since this is a surface integral, it means that we are going to use double integral. Double integral is going to cover the angle from theta and phi, because radius is taken to be r, and the equation for d comes out to be q divided by 4 pi a square into a of r, and then ds comes out to be a square sine theta d phi with a of r unit vector. Now we can simplify this. So whenever we have dot product of similar unit vectors, so it comes out to be 1, and then we can cancel a square from here. So our equation with the coefficients on the outside comes out to be q divided by 4 pi, and then the integrals are for theta and phi, and value is sine theta and d phi. So the range of theta is from 0 to pi, and for phi is for 0 to 2 pi. So we can integrate, first integrating the value of phi, that is the easiest one. So I can do that over here. So if I integrate with respect to phi, so it is going to be 0 to 2 pi d of phi, which comes out to be phi, and the limit is from 0 to 2 pi. So once you solve this, it becomes 2 pi. So I have first solved the integral of phi. Now next I will be left with theta value, so I can just solve the integral for theta. So q divided by 4 pi remains outside. I am left with 0 to pi for theta, and it is sine theta d theta, and I can bring 2 pi outside as well. So this is 2 pi, so pi cancels, and I am left with 2. So then it comes out to be q divided by q, and sine theta, when you integrate, it becomes minus cos of theta with limits from 0 to pi. And once you solve this integral, so it comes out to be, so minus, so I'm going to solve these limits, cos of pi into minus cos of 0, it comes out to be minus 1, and this becomes minus cos of 0 is 1, so negative that becomes 1. I can simplify this becomes minus 2, and then we have a minus 2, so it becomes a positive value, so I can just cancel this out. So now I'm left with 2. So this means my final answer comes out to be, when you cancel this 2 with this 2, so the value comes out to be just q coulombs. So I can say that ds dot ds is equal to q, and the unit is coulombs, and this side is proved. So I can say the equation is now proved. So this means that the equation represented by Gaussian in terms of electric flux is indeed equal to the surface charge distribution of the electric flux that equals to the charge enclosed, which is q, and hence this mathematical expression is now proven. So now let us look at some of the problems associated in finding electric flux density and electric field intensity. So in the first problem, we have been given electric flux density d with a value of 0.3 r square a of r, and we need to find the electric field at point P. So this is again the spherical systems because of the axis value. Then we need to find the total charge, which is q, within the sphere of 3, and then we need to find total electric flux with the sphere of 4. So let us see how we can solve this, starting with the first part. So we need to find electric flux density, or electric flux density is given, we need to find E. So we know the relationship between electric flux density and electric field intensity. It is equal to epsilon into E. That's it. So we can find E. That is straightforward. You just take value of D and you divide by epsilon. So value of D is 0.3 r square into A of r. So we don't need the vector, unit vector over here. It is r square into 10 raised to power minus 9 divided by epsilon is 8.85 into 10 raised to power minus 12. So what is the value of r? In this case the value of r is 2. You just incorporate the value of 2 over here. So 0.32 square into 10 raised to power minus 9 divided by 8.85 into 10 raised to power minus 12 with its unit vector A of r, and it should come out to be 135.5 along A of r volts per meter. So this is the electric field intensity for the given electric flux density. Then in part B we have been asked to find total charge q within the sphere of radius is equal to 3. Okay, so we need to find total charge q. We know that the electric flux is equal to the total charge. This is the equation that we have. Now in order to find q, we also know that electric flux can be represented as closed surface integral of ds into d of s, right? So we can do this integration now. We know that d of s is 0.3 into r square. So let me write the value 0.3 into r square. This is going to be d of s into a of r, where the value of r square in this case is 3. So it is going to be 3 square into a of r. This is the radial direction, and now I need to figure out what is d of s. So d of s again for the surface charge comes out to be, so I'm going to write it as r square sine theta d of phi into a of r. So this is the surface charge distribution. So this means I can now complete my integral as phi equals to q, which is equal to double integral d of s into d of s, with this is theta and this is phi. So it comes out to be 0.3 multiplied by, or I can do one thing, 0.3 into 10 raised to power minus 9. I have this r square and I have this r square, so I am not going to incorporate the value of r equals to 3 now. For the time being, I'm not going to use this. I'm going to multiply this two terms, it becomes r4, and then I'm going to have sine theta d theta and d of phi, and this unit vector ar with this unit vector ar equals to 1. Now it's simple integration, so I can first get rid of theta. No, let's go with phi. So if I integrate the value of phi, it comes out to be, so if I just integrate from 0 to 2 pi d of phi, it comes out to be 2 pi. So this is the first thing I get, and then I can go with the value of 0.3. So in this case I can just say now my equation comes out to be 0.3 into 10 raised to power 9 divided by 2 pi. This is what I have, and the value of r4 is a constant, it will come out, and then I can integrate from 0 to pi sine theta d theta. So let's solve sine theta d theta. It comes out to be minus cos theta with the range of 0 to pi, and once we solve this, so it will become, this portion is again what we saw previously, comes out to be 2. So this 2 is going to be cancelled with this 2, and then I'm going to be left with phi equals to the value of 3.769 into 10 raised to power minus 9 with the value of r power 4. Now the value of r in this is 3. So now if I, so this is the total flux, by the way, this is the total flux. Now they have asked what happens when r equals to 3. So now the flux comes out to be, if you put in the value of r equals to 305 nanocoulomb. So this is the answer which I am getting. Hopefully this is what we want, and this is 305 nanocoulomb. In the fourth part, we again have to find total electric flux, and this time the value of R is equals to 4. So we already know, so for the third part, we already know that the total flux is this. You just incorporate R equals to 4, let's say in equation A, which was the total flux we found. So the total flux then comes out to be 965 nanocoulomb. This is the answer. So this solves our problem, and hopefully the answer is 965 nanocoulomb. So this is the solution to this problem. Let us look at another problem, and then we'll conclude our lecture. So in this problem, we have been asked to calculate the total electric flux, which means we need to find phi, leaving the cubical surface. Now the waves are, or the flux or lines are moving away from the cubical surface formed by these planes. So these are the cubical formations, and we need to find the flux when in part A 2-point charges are provided, in part B we have a uniform line distribution, and then in part C we have a uniform surface distribution when the plane is y is equal to 3x. Okay, so let us start with the solution of this. First of all, we need to find flux for all the cases. Okay, and we need to first figure out how the cube is formed. So let us say this is the cube which we have. So this is the cube that we have, and you can see the cube has x, y, z values at plus minus 5. So this is my y-axis, this is my x-axis, and let us say this is my z-axis. All these have limitations of plus minus 5. So assume that the back ends are at minus 5, okay, for the time being. So I'm saying this is minus 5, this can be minus 5 on the back side of this cube. So these are the boundaries of the cube. So the ranges is that x, y and z are between minus 5 and plus 5. So these are the bounding for the cube, which means that if I want to calculate the side length of the cube, side length means if I want to calculate what is the total length around plus minus x-axis, so it is going to be 10. Similarly for the y and similarly for the z, this is going to be 10. This is basically side length of a cube means you just take the difference between two faces. For example, if it is for x, I know it is at 5 minus 5, so it is at 10. So this is the meter. So it is the side length, or you can say the value of L for one side of the cube. It is the same for y and z because the values or the ranges are plus minus 5 for all the cubes. So now I need to find the total charge. So I have to see whether the points provided are lying inside the cube or not. So for the first part, Q1 is having a value of 0.1 microcoulomb and Q2 is having a value of 1 by 7 microcoulomb, and the first charge is lying at 0.1, minus 2 and 3, and the second is lying at minus 1, 2 and minus 3. So I can see that Q1 is 1, minus 2 and 3. So Q1 is somewhere over here and it is lying inside the cube because it is not crossing the value of plus minus 5. Its value is plus minus 3 for the second. Similarly for the second one, it is again in minus 2 range, so it is going to be minus 1, 2, it is going to be somewhere over here. So both the charges are lying inside the cube. This means that the total electric flux will be the sum of flux from 1, flux from 2, that is charge Q1, plus charge Q2, that is 0.1 microcoulomb plus 1 by 7 microcoulomb, and it should be 0.243 microcoulomb. So this is the total flux present inside this cube with boundaries of plus minus 5. So this is the solution to the first part. Now let's come to the second part. In the second part, we are given a uniform line charge of pi microcoulomb, and it is located at x is equals to minus 2 and y equals to 3, and we need to find the total electric flux. So for the second part, again we need to find the total electric flux, but this time the line charge is given at x is equal to -2 and y is equal to 3. So x is equal to -2 and y equals to 3. Let us first draw this line and see where it is. So we have the xyz, and this is the origin, and now the line is at -2 somewhere over here, -2, and y is equal to 3, maybe this point. So the line is parallel to the z-axis. So this is the line of charges or line charge distribution parallel to z-axis. Its value is rho of L, which is pi microcoulomb per meter. So now I need to figure out what is the charge enclosed. Now if I again look at the values, I can see that my line is basically lying on the z-axis and it is inside the boundaries. For example, if this is my cube and this is my z-axis, okay, so its maximum ranges are +5 to -5, and you can see that the line is parallel to z-axis, but it is within the range, it is not crossing the value. So the line is somewhere parallel to the z-axis. So this is the line parallel to the z-axis, but it is inside the cube range. So this means that I can simply apply the equation that the line charge distribution is basically equal to the charge per unit length of the line, which means I need to find Q. So why I need to find Q? Because this equals to the electric flux. So Q is equal to rho of L into L. Now this L is basically the side length of the cube, which we found over here, which is 10 meter for any cases of x, y, and z. This is along z, so it is going to be 10. So I can say my equation is going to be pi micro multiplied by 10 meter, and it comes out to be 31.4 microcoulomb. So this is the electric flux for the line charge distribution, keeping in mind that length is basically the cube side length. Now let us look at the third part. The third part says we have a uniform surface charge sheet of 0.1 microcoulomb on the plane y is equal to 3x. Okay, so we have the surface charge distribution value of 0.1 microcoulomb per meter square for the third part, and the sheet is at y is equal to 3x plane. So this is where the sheet means. This means that the z-axis is going to be placed on this, or y is this is basically y equals to 0 plane. So at this point it is y is equal to 3x plane. So if I try to draw it, let's say this is my y, this is my x. I need to first figure this y is equal to 3x plane. So if my y is 5 and my x limits are also negative and positive 5, so what is going to be y is equal to 3x? So plus 5 is equal to 3x, x is equal to 5 by 3. So if y is equal to 5, x equals to 5 by 3. Similarly, if y is equal to -5, it is going to be -5 by 3. So the point comes out to be over here. So if y is equal to 5, let us assume this is 5, then x is equal to 5 by 3. So I can find the total distance from here using the Pythagoras theorem. This means I can say that the hypotenuse, in this case, this is the hypotenuse, is 5 square plus 5 by 3 whole square, and it comes out to be 5.27. So this is the resultant that I am getting for this triangle. So if this side is 5.27, similarly the other side is also going to be 5.27. This means that the total length I am going to get now is going to be 5.27 into 2, which is 10.54. This is on the y-x plane. So my sheet is now going to be something like this. Since this is y equals to 0 plane, so the sheet is going to be something like this, and it is moving along from this point to this point. So this is the sheet which can be moved from this direction to this one if the origin is such. So this means that I am basically looking into my z-axis with bounds of +5 and -5. This means cube length again is going to be 10. So I can find that the surface charge distribution is the ratio of charge per unit length of the surface, or I can say it is equal to the surface that is covered or the side length. So the charge then comes out to be rho of s into the total side length. Let us call this s over here. It is going to be 0.1 into 10 raised to power minus 6, the value of surface charge distribution, multiplied with 10.54 and then multiplied with the side length of 10. So it should come out to be 10.54 microcoulomb. This is the electric flux density. So again, the important point here to note is what the sheet looks like, and since it is along the z-axis or in the bounds of z-axis, so the side length of the cube is involved here, and this is the value of 10 which we saw previously, and thus this is the solution of this problem, keeping in mind that the side length plays an important part because the question has given us this bound of xyz to be ±5. So this concludes today's lecture.